This video is the masterclass for AQA Physics on Combined Science Paper 1. And we're going to cover the key components of that exam. We're going to break it down into 4 short masterclasses, the combination of which will kind of take you through everything that you need for Paper 1. So without further ado, let's get into it. The first paper consists of 4 main topics, the first of which is energy. The other 3 are electricity, matter, and radioactivity or atomic structure. So in this video, we're going to focus specifically on energy and the components of that and helping you maximize your marks in this section. So this just shows you the specification for what you are required to know and the key equations for this particular topic. It's really important that you understand that all of these equations are given to you on the data sheet, but the way that you need to use and manipulate them may not be given in full, so we'll talk about that as we go. And the specification outlines some clear examples of scenarios you should be able to explain and describe, particularly an object projected upwards, an object hitting an obstacle, or an object being accelerated by constant force, a vehicle slowing down, or bringing water to boil. So those are the main kind of examples. We'll break down the rest as we go in. And you have to be able to do calculations using these equations, which is a key skill for this particular section. So when we talk about energy, the most important concept to understand overall is the idea of the principle of conservation of energy. Energy cannot be created or destroyed, only transferred. But the underlying idea of this that's most important is from a mathematical point of view is what goes in must come out. In other words, the energy at the start of any interaction must equal the energy at the end. And all we need to do is to describe what happens to that energy at the start, what store is it in initially, what store is that energy transferred to, and when we are defining a store, we are defining that as a measure of joules that we can associate with a given form of energy, and that energy is being transferred between. Okay, so we measure energy in joules, and it's really important to have it in mind that the phrase work done and energy transferred are interchangeable when we're trying to understand the process of energy transfer and what is going on. Now the actual work done equation, which is work done is equal to force multiplied by distance, is actually listed in a specification in the module P5, which is the forces module, which is actually in paper 2. However, the principles that underline that equation can still be relevant to the equations in this topic. Okay, so it's important just to have that in mind. So first, it's important to understand clearly what we mean by the energy stores, and the point that people get most confused about with energy stores is they confuse them with the energy resources, so I'll highlight the difference between those in a minute. But first off, when you are revising the energy stores, the most important thing to understand besides just the revision of them is what question do you ask yourself linked to each one. So for gravitational potential energy, the question you must ask yourself is, how high is the object? So if the height is increasing, gravitational potential is increasing. If the height is decreasing, gravitational potential is decreasing. So gravitational potential, just link in your mind to height. Any question, any scenario where height is changing, gravitational potential is changing. For kinetic, the question you ask yourself is, how fast is it moving? The faster, the higher the kinetic energy, the slower. You get the idea. Chemical potential, the question you ask yourself is there a fuel? So any scenario, any question where there is a fuel, particularly when there's a chemical reaction taking place, that fuel is being consumed, that means that the potential chemical potential energy is going to be decreasing. There is a scenario, for example, where chemical potential could be increasing, and that would be if like a battery was being charged up, for example, because batteries also have chemical potential energy as the store that they start with. Probably the most important energy store to have in your mind, if you don't learn anything else in this topic, is thermal. Thermal is the one that will occur in pretty much every question that you get, because all energy ends up fundamentally being wasted or dissipated as thermal energy. So the key question you must ask yourself with thermal energy is, what is happening to the temperature? Is it getting hotter or is it getting colder? If it's getting hotter, thermal energy is increasing. If it's getting colder, thermal energy is decreasing. All of the others are there, but are less important, quite frankly, because they're all very context specific. So obviously, if the question involves a speaker, sound will be involved. If it involves a light bulb, light will be involved, etc. Obviously, or a chemical reaction might also involve light as well. Elastic, the question you ask yourself is it changing shape? Okay, and obviously nuclear really is only going to be applied in the context of nuclear power stations. One note to misconception to be aware of in this is electrical is not a type of energy store. There is the electrostatic store, which is the electrical energy or electrical potential energy that is associated with the position of two charged objects in relation to each other. But an electric circuit is not an energy store. An electric circuit is rather a mechanism for energy transfer, which is not the same as an energy store. So, if we think about, which I'll come back to that point in a moment. So, when we think about the energy stores, we can divide them into kinetic types and potential types. So there are 4 potential types: gravitational potential, chemical potential, elastic potential, and nuclear potential. And all of the others at some level have something to do with some form of movement. So even like heat, for example, is linked to obviously temperature, which is to do with the kinetic energy of the particles. So it all kind of links back at some level to some form of movement. So we kind of divide them loosely into those categories to help us remember them. But please make sure it's really clear in your mind the difference between the stores and then the energy resources. So a really common mistake people make is they're asked about the stores and they start talking about resources. Resources are basically the methods of generating electricity. How do we generate it? So hydroelectric power, wind turbines, fuel, tidal, solar, etc. So have that really clear in your mind. The stores are focused on for the first half of the module. The end of the module focuses on energy resources. We will circle back to those at the end. So building upon this idea of the energy mechanisms of energy transfer, understand that when work is done and energy is transferred, there are 3 mechanisms of energy transfer. This is not the same as the stores. This is how we transfer energy between the stores. And the 3 ways we can do that is we can use forces, which we describe as mechanical transfers. So that force, for example, could be used to raise or lower the height and the speed of an object, and therefore the transfer is happening between gravitational potential and kinetic energy. But because forces are the thing causing that energy transfer, it is a mechanical type of transfer. You can have thermal transfers, and that occurs via conduction, convection, and radiation. And then there are electrical transfers, i.e. circuits. So in that scenario, that highlights how electric circuits are a mechanism of energy transfer, not a store in their own right. Now, when we think about just expanding upon the idea of mechanical transfers, which is what the main focus of the first module is actually on, we have to think about what the effects of forces are. So there are 4 effects that are possible when we think about the resultant force on an object. Those 4 effects are: it can speed up, accelerate; it can decelerate, slow down; it can change shape, which is known as deformation; or it can change direction. Okay. Now, of those 4 scenarios, in each case there is a different energy change that occurs. Forces are causing all of them, so they're all methods of mechanical transfer, but the store that changes will be different in each case. So if it's acceleration and deceleration, that is clearly a change in speed, and so the kinetic store will either increase or decrease. Examples of that might be a rocket launching initially, or say a tennis ball hitting the ground, or a car braking. Remember, one of the examples that was mentioned in the specification was about an object hitting an obstacle. In other words, it will be caused to decelerate. Anytime the object changes shape, then that is a change in the elastic potential energy, and obviously that can increase both in the scenario of extension and stretching, or in terms of compression. Okay, so it can work in both directions. And any change in height causes a change in gravitational potential energy. So if any of those things result in that, then we get that. It's worth noting that a change in direction does not actually do work, because the force is applied perpendicular to the direction of travel, and therefore no work is done, and therefore the actual energy transfer is not applied. So just as a side note for that. So one really important scenario to kind of have clear in mind is being able to describe the interplay between kinetic and potential energies, and this also brings us to what mathematically might be the most challenging parts of the module. So when we think about this scenario, you can see the questions that are on the left, like when is potential energy greatest and why, when is kinetic energy greatest and why, where is that energy coming from and going to, and are there any other stores that are not included here. Now, the things that you should be thinking about for that, feel free to pause the video if you want time to think about it, but is that when it is at the highest point, you can see the blue bar increasing. So remember, anything linked to height we associate with potential energy. So as anytime it's moving up, potential energy increases. Obviously remember that's gravitational potential energy. Anytime it drops, like in that moment, potential energy decreases. Kinetic energy is greatest when it's travelling fastest, which is always going to be at the bottom of each of those points. So you'll see the green bar be highest at the bottom there, at the bottom here, and as it comes back round, again at the bottom there. And then obviously it slows, because the other store that's not included here is thermal energy, because remember, all energy is wasted and dissipated as heat. But for the purposes of calculations, we often ignore the effect of that friction, both with the surface and with air resistance, or drag, in order to make the maths easier, so we can make potential energy and kinetic energy equivalent to each other, which I will show you in a moment. Other examples of this scenario would be like a pendulum bob, okay, so you need to understand how to explain that, okay. It's worth pausing the video here and just having a little think about this, but I'm just going to show you very briefly the key points that you should understand, which again come back to the same key ideas of when is it at the highest point and what is the speed. So at the both ends of the pendulum, that's when kinetic energy is at 0 because it's stationary, and gravitational potential energy is at a highest point. Kinetic energy is maximum at the bottom because that's the lowest point, and that's where all the energy has been converted into that, minus the small amount which is of course going to be lost as a result of friction. So we understand the idea of how the store increases and decreases at each phase in the pendulum. If you need to spend longer studying this, then I encourage you to pause the video and take a little bit of time to consider this problem. So some other examples that you should be able to describe, I'm going to blast through these really quickly, and each one feel free to pause and spend longer to think about it and study it. But I just want to highlight some key points when we're thinking about energy stores increasing and decreasing. So firstly, the first point I want to make is that pretty much in every scenario we can think about one of the 4 potential stores is going to decrease, because typically that's where energy in the truest sense of the word is actually stored, if there is such a thing. So for example, any time there's a fuel, we start with a chemical store, so it's very common to start with a chemical store which is going to decrease, and that energy is going to be converted from the fuel into other forms. So in the case of like a combustion reaction, that would be light and heat. So the thermal store of the surroundings is increasing here, as is light, and the chemical store is decreasing. Another example of almost the same thing would be like a drag car race. Again, it's a fuel in the engine, so the chemical store is what we start off with, and that is generating not light this time, but heat and kinetic energy. But it's the same basic idea. And then fundamentally, at the end, all of that kinetic energy is going to end up having that energy be dissipated as heat, both to the friction with the tyres, the road, the brakes, and the surroundings. Okay, so we need to consider that's fundamentally where all energy will end up. And a really important point, I think, is this example, which is a cup of tea cooling down. And this highlights the point that you can have the same energy store be both the thing that is increasing and decreasing if we are specific about locality. So the thermal store, in this case, is decreasing in the water because the water in the tea is cooling down, but the air around it is warming up. And so whenever we identify a thermal store, an extra exam tip here is always be specific about the location. What is increasing in temperature and what is decreasing? And always ask yourself that question. What's getting hotter, what's getting colder? In the case of like a bungee jump, in this case we start off with high gravitational potential energy because we're high up, and that is converted into kinetic energy as they fall. The elastic potential energy doesn't start to increase though until the bungee cord is actually getting stretched. So at the very bottom of this ascent, you can see the tension in the cord begin to sort of straighten out, and it's not until that point where elastic potential energy increases. That only increases when the actual bungee cord is actually stretching. But the result of that, which you can better see here, is as it stretches, the person's going to slow down, so their kinetic energy will decrease, and their gravitational is decreasing the whole time because they are falling. Now, of course, when we think about the flip side of that, which is what happens on the way back up, then in that scenario, the elastic potential energy, which is a maximum when it's stretched, is being converted back into gravitational potential because they're getting higher, and back into kinetic because they're being accelerated back upwards. And again, the thing that's not shown here is that fundamentally all energy will end up being wasted as heat. So, in terms of calculations, the first thing you should be able to do for this is to use the equations in a simple form. So I'm just going to give you some really quick, simple examples of some calculations, and if you want to work these out, feel free to pause the video and spend a little bit longer on them. But the equation for gravitational potential energy is mass times gravitational field strength times height. Remember, on Earth, gravitational field strength is 9.8, so the mass and the height are the two variables in here that are most likely to change in most questions. So remember, anything when we're thinking about gravitational potential energy is about the energy due to position of an object within Earth's gravitational field, or the gravitational field of another body. And so fundamentally, how high is it and how much mass it has are going to be the two main things that are going to affect that. Of course, if you went to a different planet, then of course that would also make a difference. So if we think about what it would be for this tennis player throwing the ball upwards, okay, we would think about the fact that the height of the ball is increasing, and so gravitational increases on the way up, and obviously as it falls, it would be coming down. Now, kinetic energy, which is half mv squared, again, mass is an important factor there, but this time speed is the most important because we've got this speed squared. So remember, don't neglect the role of mass in both of these equations, but height and speed are the two main variables that you will focus on. So an example question that you might want to do for this is just to work out what the kinetic energy of a bowling ball would be. So feel free to pause the video at this point and have a go at that calculation. I'm going to put the answer up now. So when you write out the variables, write out the equation, put the numbers in this particular case you get 130.68 joules. So a nice simple calculation for kinetic energy there that you should be able to do. Another equation that comes up in this topic is elastic potential energy. Remember there are two equations for that, half Fx and half Kx squared, so you should be able to use both. K is the spring constant and X is the extension, F is the force applied on the spring. Again, here's an example of a simple calculation you can do for this, but in this there's the added issue of giving your answer in millijoules. Again, please feel free to pause the video and have a go at this. The answer in this particular case is 91 millijoules. So those are simple examples of calculations that I hope aren't particularly difficult as long as you know and recognise the equations. If you don't, then please use the datasheet to help you. I just want to mention very briefly what is the harder version of questions that you can get in this particular exam, and that is when the energy types are made equivalent to each other and we have to apply the principle of conservation of energy. So remember, energy cannot be created or destroyed, only transferred. So imagine this question. If we've got a tennis ball leaving the hand at 5 meters per second, we've got to calculate the height that it reaches above the hand. So how can we do that? Well, we need to think about the energy that it has initially, which is the kinetic energy, and then the energy that it has as a result of height, which is gravitational potential. So that's us understanding the stores that are involved, and obviously we can relate those two stores to the equations as we know them to be, so half mv squared and mgh. Now, one approach to this question, and I'll show you this in a different question in a moment, is we can deal with each of those two equations separately. We can start off by working out the kinetic energy, and then we could work out the gravitational potential energy as a result of that. But there's a problem in this question, which is we've not been given the mass of the ball. So one way we can resolve that is by making the two equations equal to each other. So we say that all of the energy is converted from gravitational potential into all the energy is converted from kinetic into gravitational potential. And that, of course, is assuming that we're ignoring friction, so there's no energy wasted here. But we can then make half mv squared equal to mgh. When we do this, you can see that mass is on both sides of the equation. So we don't need mass because it will cancel on both sides. And so what we therefore end up with is two versions of this equation when we rearrange it. Either h is equal to v squared divided by 2g, or v is equal to the square root of 2gh. So what that tells you is that actually anytime you know the speed, you know the height that it will reach, or anytime you know the height, you can work out the speed, because the 2 and the g are both constants. So g is obviously 9.8, and unless of course it's on a different planet, so that bit will never change. So if you know one, you know the other. Now you could just learn those two outcomes, they're not given to you on the data sheet, so worth just remembering. Or alternatively, you can understand the process and just work it out in situ in the exam. But if we put numbers into this, for example, we would get the answer of 1.28 meters. A different example of a question that's very similar. So let's imagine that we're applying it to this kind of roller coaster sequence, okay? You can pause the video here and have a go at this if you want. This has been broken down into three 3-mark questions, but feel free to have a go at each. So in terms of describing the energy changes, I'm not going to dwell on this, but again, it emphasises the point that gravitational potential energies are maximum at the highest points and kinetic energy is going to be maximum at the fastest points, okay? Remember, friction is going to result in thermal energy store increasing over time. When we apply the equations, the approach this question has been given, because you have all of the information, as opposed to the example of the previous question I just showed you, is to work out gravitational potential energy first. So you can see all the information that's given in the question is used to do that. You obviously need to remember that gravitational field strength is 9.8, and then use that number that you've calculated then in the kinetic energy equation to then fundamentally work out the velocity, because we know the mass in both cases. So you can apply that approach, like that two-step approach, but this kind of multi-stage calculation is one of the harder things that you can be asked to do in this exam. Two other less common examples of this, but that you need to know, would be what happens if you make elastic potential energy equal to gravitational potential. So in this particular case, again, you can have a go at this problem, but we make these two equivalent and we go through this very similar process of either working it out in two separate stages, so we work out elastic potential first and then gravitational, or we can make them equivalent and do it in one go. So either of these approaches, when you have all the information possible, you just need to decide what you prefer. Feel free to pause the video and take a little bit of time studying this question if you want to spend more time on it. And another example, again, feel free to pause if you want to have a go at it first, but in this question, we're making kinetic energy equal to elastic potential. And again, if you want to review the two possible approaches to this answer, to this question, there they are. Feel free to pause the video to spend a little bit longer looking at that. Now, this skill, it's important to stress, is not something that you need to worry about if you're doing the foundation paper. This skill is much more likely in the higher paper. In the foundation paper, any one of these equations is likely to come up in isolation, but probably not all combined. In the higher paper, this is much more likely to occur. Whether that is for combined science or triple. Now, the middle part of this section is the end of the energy topic is about the practical, and the practical is all about determining specific heat capacity. Specific heat capacity is a key part of the first exam because it's covered in both this module and in the matter module, so it's likely to come up effectively twice as likely. So specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. In other words, how much heat energy can an object hold, can it store? And so if we're trying to investigate that, or trying to work it out, we need to take some measurements. So the practical that you need to be aware of is particularly how we can work out it for metal blocks, or we could also work out specific heat capacity of liquids. So either of those two scenarios you should be aware of. Now, depending upon the equipment you're given will depend upon the precise way you'll carry out this practical. So just some general considerations that I want you to be aware of. So in this practical, the independent variable, the thing we change is we transfer energy either to the metal block or to the liquid we are trying to work out the specific heat capacity of. And we actually need to measure several things, not just temperature, but in the first instance we are tracking the temperature if we're going to plot it as a graph. Now, if you're doing the full version of this practical, I would say to you that there are 5 things that we have to measure, and it's really important for you to be clear about what those are. So we need to measure everything that is in the specific heat capacity equation, okay? And some of these things will be control variables, but nevertheless we still need to measure them. So we need to measure the temperature change that occurs, so we have to measure temperature, and then we'll use a thermometer to do that. We have to measure the mass of the block, and obviously we'll use a balance or scales to do that. If we are doing this with a liquid, again we need to know the mass of the liquid. You also need to know how much energy is being transferred to it. Now, you can measure energy using a joule meter, but if you don't have that, an alternative, which is often included, is you can work out the energy transferred by doing power multiplied by time, and work out the power by measuring the electrical power to the heater. So in that scenario, we need to measure, in addition to the temperature and the mass, we would need to measure the current, we would need to measure the voltage, and we need to measure the time. And we would do that with an ammeter in series, a voltmeter in parallel, and a timer. So being super clear about the 5 things that you're trying to measure and the 5 pieces of equipment are essential for you to get marks in this particular question. So this is one example of like an apparatus list, and you can see an ammeter and voltmeter is included here, as is a stopwatch and a balance. So you can see the equipment in this particular list is obviously for you to measure those 5 things that I've just talked about. Okay, remembering you need to remember that ammeter must be connected in series and the voltmeter in parallel. A version of the diagram for this might look something like this. Okay, so this is one example. For you to have a look at about how you might draw the thermometer in the metal block, have the heater inserted, the voltmeter in parallel, the ammeter in series, and obviously the thing not shown in the diagram is the timer, which you must write separately and show. This graph shows an example of the kind of results that you might get from the specific heat capacity practical. Notice that there's a slight upward curve at the initial start of this, where obviously there's a delay between the time of the heat going from the heater to the thermometer. But then after that, where it's a straight line, from that point you can then work out the gradient, and from that you can work out specific heat capacity. So if we are doing this, obviously remember gradient is always the change in y divided by change in x, and that approach, the gradient you'll get in this particular example would be 0.028. Obviously you need to take a bit of time to work that out, but the gradient of the specific heat capacity is 1 over the gradient, so you have to do 1 divided by that number to work it out. So in this particular case, the specific heat capacity would be 357. So that kind of question is a little bit more tricky, so I'm not going to spend a massive amount of time on that right now, but just know that that is something you could be asked to do if you're given a temperature and energy graph. Here is another example of that kind of data and an explanation that goes with it. I'm just going to leave that there for you. Feel free to pause it and have a little look at that as you go. So the last section is therefore about energy resources. So I'm going to fly through this really quickly. What I'm going to encourage you to do is to pause the video and to have a little bit longer to study some of these ideas. So first off, some basic definitions about the difference between renewable and non-renewable energy resources. The key word to have in your repertoire here is the use of the word replenished. Can it be replenished or not? That's the thing that makes it renewable or non-renewable. So you should be able to describe in simple terms the basic stages of a conventional power station, and that effectively is that fossil fuel is burnt in a boiler to produce steam. So we turn water into steam. That step can vary in different contexts, but then the bits after that don't really ever change. So we then have a turbine. That turbine rotates. That turbine is connected to a generator which produces AC electricity, which is one of the features of mains electricity you need to know. That's then connected to transformers, which are designed to efficiently transport electrical power between the national grid, through the national grid, between the power station and your home. That process will vary if it's a nuclear power station, but only on the first stage. So instead of it being a chemical reaction, a nuclear power station would be a nuclear reactor that, again, generates heat, which turns water into steam, and then everything else is exactly the same. Obviously, other types of power might focus on the starting with the turbine, so for example, like a wind turbine or tidal power, hydroelectric, all start at that stage. There is just no boiler involved. So when we think about non-renewables, okay, we're thinking about fossil fuels or nuclear fuels, and generally we can summarize the advantages of these as things like, for example, historically they've been very cheap, geographically available, they're not weather dependent. Those are all things that will kind of contrast those to non-renewables, which we'll look at in a second. With nuclear in particular, they have the advantage of not producing CO2, and they produce a large amount of energy. For any of these, you should also know some general disadvantages. So for your fuels, your chemical fuels, of course, you do produce CO2, which is a downside, and also other impurities like sulfur dioxide. They can also produce visual pollution, and obviously as supply runs out, they're becoming more expensive. With nuclear power, you have the disadvantage of nuclear waste, which you must dispose of, and the risks of contamination and nuclear disasters. If we contrast that to renewable energy sources, so you should know a broad variety of these. So for example, solar power, wind, tidal, wave, hydroelectric, and geothermal. There is only one renewable fuel, which is biofuel, which obviously comes from burning biomass. And each of these, just as I'm linking this back to stores again, are basically converting a different form of energy store into the kinetic energy, which is driving the turbine to turn the generator, and the rest is kind of the same. So just be aware of that with one variation. We can summarise these in simple terms of general advantages and disadvantages again, which are generally they don't produce CO2 or carbon dioxide, they generally have much lower running costs, they generally are obviously renewable. The disadvantages are issues around weather dependency, unreliable power output. They can be expensive at outlay, particularly things like hydroelectric. They can potentially damage the environment during construction, and they have a degree of visual pollution. Some are geographically restricted, like geothermal, or for example solar power obviously is not particularly effective in regions where it isn't sunny. And biofuel, again being a fuel, has one unique disadvantage, which is it does still produce CO2 because it's still a combustion reaction. So a bit of extra information about biomass and biofuel is listed here, and about carbon neutrality. I would just pause this, have a quick read of it, and then move on. The last bit I want to mention about this topic is you are highly likely to end this section with questions that are data-related questions. Those data-related questions sometimes are about UK energy generation, and other times are about global energy generation. So you can see this example of different energy resources on a global level, and the factors that are associated with that, such as population increase, increase in vehicles, and increased electricity demand. Here's another example of a 6-mark question that is on this topic, and the mark scheme for this I will put up here straight away so you can have a look at it. But the thing I want to highlight to you in this particular bit is that you are highly likely to get a question where you have to do this data analysis. So what I want to end with on this section is to give you some advice about the data analysis questions. So the first thing that when you get a data analysis question that you need to do is make sure you pay particular attention to the axes and spend time studying the graph or that you're given and the information. So here, take the time to work out that the black lines are 2013 and the grey lines are 2018. So think about the fact that you're changing between those 2 years, and the scale of the axes. So from this example, it is in terawatt hours. is like in terms of the amount of energy generated, so you can talk about that. So take time to familiarise yourself with it. So for example, I might annotate on here that coal, oil, gas and nuclear, the first 4 are all non-renewable, and then the 4 after that are all renewable, so wind, solar, biomass, others, or hydroelectric. Then we want to focus on some data points that we need to pick out. So always look first for extremes. What is the highest, what is the lowest of anything? So you can see in 2013, the highest used energy resource was obviously coal. You can also see that the biggest change between any 2 points is coal. Between 2013 until 2018, it's decreased massively. So look for the highest, the lowest, and the biggest changes. Those are always things to kind of worth putting in straight away. The second thing, after you've looked at the extremes, you want to look for is you want to begin to identify what's the general trend. So what are the general patterns? So you can see that in each case that there is, for the renewables and the non-renewables, so for example, if you look at the 4 renewables, you will see that the general trend is that all of them, apart from hydroelectric, increased between 2013 and 2018, and the general trend for non-renewables, is they decreased. Now, in both of those cases, what you can also see when you look at the general trend is you will pick out the next bit, which is look for anomalies. There will always generally be something that doesn't fit the pattern because they want you to pick that out. So you can see, for example, that gas is an example of a non-renewable, which has actually increased, and hydroelectric is an example of a renewable, which has actually decreased, which doesn't fit the general sort of trend. The last thing to check for is then to think about the pattern and to make sure the difference is clear to you between trends and patterns. Trends are general, patterns are specific. So the kind of thing you're going to do when you think about the pattern is actually quote some numbers from the data. So for example, you might say that coal has decreased from 130 down to 17 terawatt hours in that time period. So you can be a little bit more specific, or maybe if there's a particular change in other types of data, like a sort of scatter graph, for example, you might describe the effect of that not just as being increasing or decreasing, but the rate at which it's increasing, how that might be changing, or if it's increasing constantly, or if it's random. That extra little bit of detail, that's what makes it a pattern, that extra little bit of specificity. So I hope that helps the first module, the first section, which is P1. Check out the other masterclasses on the other modules that are going to help you prepare for your Paper 1 physics exam.